Okay, today we'll be doing combination sum, which is a backtracking problem. So let's read the problem. Combination sum. You're given an array of distinct integer nums and a target integer target. Your task is to return a list of all unique combinations of nums where the chosen numbers sum to target. Okay, so we'll have to build a list. Okay. The same may be chosen from nums from an unlimited. The same number may be chosen. Okay, this is probably what's going to make it difficult. You can choose a number multiple times. Two combinations are the same if the frequency of each of the chosen numbers is the same. Otherwise, they are considered different. You may return the combination in any order, and the order of the numbers in each combination can be in any order. Okay, this is gonna be a bit tough. So I'm thinking of using like a DFS and just kind of like every time we go down a path, we can use the number itself and add it up. So I'm thinking of using DFS on backtracking, just creating a res array which we will append each subset to, and we'll try every combination, which includes the number itself as well as the other numbers as well. Backtrack. In this case, I should probably use the index to keep track of where we are. Subset, which is the array that we're building. Target, we can remain as if. If I'm missing something, I'll kind of go back. And I guess if some subset. Okay. I'm not sure if sum has a time complexity of O of n. If it does, I can always like make like count here or like current sum. But I'm just gonna assume it's not O of n for now. And wait, let me just check. Is sum in Python O of n? Okay, it's O of n. Okay, then we're not gonna do that. We can just do like yeah, we can just make sum like curSum. This is like the current sum at the moment. If curSum is greater than or equal to target. Okay, let's just do, if it's equal to target, we can just append the current subset, and we're gonna create like a copy. We can even return, I think. If curSum is greater than target, then we just return. So now res.append. So we're gonna use the backtracking function with curSum plus equals nums I, which with the current number, and we're gonna include, so we're gonna include current number and exclude current number, which is, we basically have like two choices that we can make, which is to include this or to move forward, right? Because we want to go through every possible combination. So we're first going to add the number, backtrack I, subset is, I should actually append that, subset.append nums I, and curSum. Now we exclude the number, it would be backtrack I plus 1 because we're advancing the index, subset.pop, and actually let me just do it here, subset.pop, and curSum minus equals the nums I once again. So Then we can just call it again. And I think we should be good. We do want to return, this is the kind of condition. We make a choice of whether we want to add the current number again or to move forward. Okay, and then let's call the function index 0 subset curSum. Oh wait, subset should be an empty array. curSum should be 0. Do I need len nums? Or I is greater than len. I is equal to len nums, yeah. So I feel like this is also another condition that can happen. Whenever we hit anything above that number, we want to go back, because at that point it's like there's no point. Don't know if this should be good, but it doesn't hurt to try it out. And I'll even add some print statements here to kind of like walk through it. How would I do this? Print res. Print I subset curSum, I guess. Print I subset curSum. I can even do that. And I'll add like include, so I know where this is. Exclude. Final res. Alright, let's try this out. Oh, what the hell? Actually? Nice. Oh my god, I did this in one go. Absolutely lovely. Wow, I did not expect to get that so quickly. Nice. So, not sure if this is the optimal solution, but let's think about the time complexity. So, time would be, let's see here. Basically going through like n. What would it be? I'm backtracking through every possible combination. I'm tempted to say n log n or something. Okay, yeah. Alright, I kind of struggle with the time efficiency here. Space complexity would be, I don't know. It would be res. Only res would need to be taken into account. What would that be though? Like a possible combination. It'd be very similar to the time complexity. Right, space complexity is 2 to the power of t over m. Okay, whatever that is, bro. Maybe there is a way to kind of just the minimum value in the array. What? Okay, I think there might be a more efficient way of doing this, so let's take a look at that. But for now, I don't even know what time efficiency this is. I'm gonna have to like ask ChatGPT, dude. But we got it. I don't think it's optimal though. Time and space complexity. It's backtracking. Yeah, so we either include or exclude. And it looks like, oh. The maximum time complexity is this, basically, which is actually that. So 2 to the power of TLM. And the reason why it's 2, it's like you could either include it or exclude it, but I don't know where this came from, t divided by m. space is NTM. T over M. Yeah. Why is that? So yeah, I understand that you can either include or exclude a number, but why? Oh, okay, I see it. Because the least number, we're thinking about the worst case scenario here, in which case it would be target divided by the lowest possible number, because we can include that number that much times, that many amount of times. And same thing with space complexity, I guess. That much number, M amount of times. Max depth, basically. Okay. All right, I kind of get it. Let me look at the solution. Oh, they sorted it. It's about the same, though. Yeah, it's the same. What is the difference? Yep, okay, total screen, yep. Return. Cur.append, yep. Yep, oh, okay, well. There you go, very nice, wow. Okay, wow, that's very good actually. Nice. Yeah, that should be it. Pretty fast one for today. That's good.